So this is frozen data structure in C++ 14. I am Serge Guelton from France, and we're going to spend 1 hour together, maybe a bit less. Please keep the question for the end. And before I begin, I'd like to state that even if I am the one here, and I'm the one that started this project, I got quickly surrounded by 3 smart people, probably smarter than me in their own fields. So I'd like to thank Chris Beck for all his job on the random stuff, Jérôme Duman for hashing, and Jérôme for all his code lifting, and Austin for his CMake knowledge. They all are much smarter than me. So let me introduce myself. So as a daily job, I work for Quarks Lab, which is a security firm based in France, and I'm building an obfuscating compiler based on LLVM for them. We're going to present it at the tool session at the end of this day. So if you're just puzzled by what does obfuscation mean, we've got some intro for you. I'm also an associate researcher in a French engineering school, a happy developer of an open source project, Python, that converts numerical Python kernels into C++. I do occasionally commit to LLVM, and I am the proprietor of 2 girls, so Nihao, Xiaolei, and Lucy. So that's for YouTube later. And I'm saying that now because all these points have an influence on the library I presented. When you design a library for performance, it helps to know the internals of a compiler. When you name it frozen, so it has nothing to do with some very famous license. It's based on the Python package called frozen set. And the frozen set in Python is just like a set, but you can't add elements in it once it's created. And that's the seed of this library. Being an associate researcher means that I occasionally read papers of people that are smart, and I get to understand part of them, and it helps to implement because I'm basically an engineer. And being a father means that you still have watched a lot of Disney films, and repeatedly, so it has an influence on the naming of some parts of the library. Before we really start, whenever you see code compiled or benchmarked, it has been benchmarked on this very laptop, compiled with not so recent version of GCC, but that's the one shipped with my Debian machine. And all the benchmark have been run with Google Benchmark. So if you're familiar with the layout, you will easily interpret the result. So, shall we begin? When you write const, the const modifier, the const qualifier on a variable, it means you can't modify it, or you should not modify it. Does it mean more than this? If I declare an std array, const, and initialize it, I declare it extern here because otherwise I don't have the symbol in my object file. Okay, that's the only content of the file is this. If I compile that, and I have a look at the object code generated, I do have a read-only data section. You will see occasionally this kind of objdump things. It's because I'm surrounded by reversers in my daily job, so I tend to use that. If you don't understand this, there is a talk about the ELF format tomorrow, presented by me, so you can come. That's some trailer of what will happen. Anyway, so in this read-only data section, you will find the exact bits that have been put into the array. So that's what I like with C++. You declare some kind of high-level looking types, but in the end, in the right section, you have the right bits, and there is no overhead at all. Everything. And it can't be modified, it's const, it's in the const section, that's great. And if I have a look with objdump to the text.startup section, which is a place where code that runs before main lie, so typically for a static constructor, then this section does not exist because here there is nothing done at runtime. That's perfect. That's a plain old array encapsulated in a pod type. And that's good. I mean, when I declare this kind of structure const, I want that. But then I go to vector. I declare a const vector. I can't modify it. I would love having this in the data section. And guess what? This has the same value, and they are in the data section. But an std vector is not initialized, it's not a pod type. This is not the std vector content. This is the content of the initializer list that is fed to the vector. The syntax is the same, but it's not the same creation process. And indeed, if I have a look to the startup section, it's not empty anymore. All the codes that does the initialization, the allocation on the heap, is done at that point, right? So I have a container, it's const, it won't be modified anymore, but still some things are happening. So there is a cost. But well, it's a misuse of vector. So I can cope with that. But then, if I have a look to std set, I declare my set, and I have a look to the very same read-only data section, and I have the values in that order. That's 1, then 8, then 7. And we do have some initialization process. So in fact, there's not much thing happening at compile time there. Everything is happening at runtime. Set tends to be implemented as a red-black tree. And so the construction, the building of the tree is done before the main. And so you're paying for that. And if you are initializing a lot of objects, then before you start doing things, you will already have executed a lot of code. And I don't like that, because that's a good use case. I have a set of things, and it won't change. And I have told the compiler that it won't change, because it's const. But I'm paying for something I don't want to pay. And that's not the C++ way of thinking. If I summarize, I have all this basic container from the standard template library. And if I want a const version, then I can manage to have the equivalent of vector with std array. But I don't have anything out of the box for set, map, or unordered set, and unordered map. And that's a pity. I would love being able to initialize a container and say, you're initialized, and now I will just use you and won't increase your size anymore. So that's the whole topic of this presentation. I want something that looks like an std set. You remove all the members that can modify the content, and you get a frozen set. You do the same for a map, another map, and another set. But it's basically set and map have the same underlying logic. So it's really about set and unordered set. And I want that, and that's what I tried to achieve. So first, speaking about how it would look like std array that had an extra parameter, my frozen set would be initialized by a number of elements. So this number of elements will go into the type signature. And then I have the key, and I have the compare function with the extra constraint on the compare function, which is it needs to be constexpr, because I'm going to initialize my structure at compile time. And for the map, it's exactly the same thing. So first, extend constexpr. This is valid. This is a bit strange, but let's assume it's OK. Well, according to the compiler, it's OK. I'm not setting the standard. I'm setting the compiler. I declare this value. It's a construct value, but it still creates a symbol because of extern. I'm looking at the read-only data, and I have the same numbers as before. Not really, because it's not the same order. Basically, you can create a frozen set as a plain std array. It's sorted, and whenever you want to do a lookup, you do binary search. That's plain stupid, But you will see that not only it works, but it's efficient. So in my data section, I have the sorted version of the data, and I don't have the initializer list, because it's not an initializer list here. And if I have a look at the startup section, there isn't anything, because everything is done at compile time. So I have achieved my goal. Everything is done at compile time. It's read-only, and that's what I want. And it's strong read-only. If I constcast that and try to modify it, I will get a segmentation error because I'm not allowed to access this page, which will be mapped in a read-only page. And if I initialize a map, using the very same syntax as std map, with the extra number of elements, I have my data that lies in arrow data section, and I don't have any startup costs. So that's the construct, that's what I want. Okay, so I don't pay for initialization, but is the lookup faster? Well, it actually doesn't matter. I mean, if I already don't pay for the lookup, for the initialization, I'm happy. But it turns out that it's also faster. So there is some kind of name mangling in the benchmark name. So the benchmark for an integer in a frozen set or in a standard set, in a standard array, and I'm doing a linear scan, and in a standard array that is sorted, and I'm doing a binary search. Okay? And this benchmark looks for every element that lies inside the array. Okay? I have 42 keys, and I'm looking repeatedly for each of the key. So a few things. This is a very small container. So for a small container, it's faster to do a linear scan. It depends. If it's always at the end, maybe not. But in average, it's faster to do a linear scan than to use std set, because it's small. Okay? It's because the big O notation only tells you about things that it's at the infinite. And we are not exactly at that point. The binary search at that point is also almost the same as a linear scan. And our frozen set, which actually uses a binary search, but a specially crafted one, is much faster. It's easy to understand that we know the size, so we can take advantage of that to do a better binary search. If we are looking for something that is not into the set, then we are also faster by a factor of roughly 3 compared to the standard library. But it's comparing apples and oranges, because it's definitely not the same algorithm behind the hood. And even compared to a standard binary search, we're faster. We're going to have a look to that later. But that's cool. We don't pay for initialization, and we are faster for lookups. And it happens that it's even cooler. The generated binary for smaller, at least for smaller sets, is slimmer. Let's take this example. Everybody has written this kind of function that takes an enum and returns its string implementation. This is a basic implementation with a switch, and it takes roughly 6 kilobytes. If I do the same with a standard map, where the key are the enum value and the value are their string representation, and I'm just doing a lookup. So it's not exactly the same, because here I'm raising an exception if it's not in the set, while with a switch I was defaulting and probably returning null pointer. But still, it's much larger, roughly 8 kilobytes. And if I use the same code but replacing std by frozen and adding the number of elements, then I'm smaller. I'm even smaller than the enum version. And that was surprising to me. So in order to understand why, let's have a look to the binary code. So s_objump is super objump, because it adds some extra arrows to help me understand. So that's the switch version. So this make looks frightening, maybe if I do. Yeah, I'm trying to do that. I can't remember the shortcuts I had. That's why I wanted. So the important line is this one, jump Rx, which means you're doing an indirect jump, and that's how you implement a switch. Okay, there is potentially a compiler could optimize this into a lookup into an array, but it depends on whether the enum values are contiguous or not, which is not the case here. And so I'm jumping to one of the case that is visually understandable here, and then I'm doing a small addition and then returning. Okay, so that's the size grows linearly with the number of elements in my enumeration, and I've got roughly this amount of bytes for each new case. If I have a look to the standard map version, then this startup thing is the initialization process. I don't care about it, but still you have to pay for it in terms of size of code. This is the lookup. You can guess that it's a lookup because there is a lot of back edges, because there is this transversal of this recursive transversal of the tree, which is probably a while. Well, it's huge in terms of size, but it's independent on the size of the array. So probably if I have a very large map, this size won't change much, but still there is a lot of logic. If I have a look at the frozen version, it's very slim because the algorithm got specialized for this particular value in the set or in the map. And you can even see that there are a bunch of C-move and not that much jump. While when you do a binary search, you generally have a lot of jump. It's because at some point the compiler decided to use a conditional move instead of a jump, which makes the code smaller. So that was not a goal of the library, but it turns out that it's small. So that's just a good thing. Okay, before I move forward to the, so that was for SED set and SED map. And before I move forward to SED unordered set and unordered map, I need to define two notions. What is perfect minimal hashing? So hashing is I take a value and I convert it to some kind of integer. Perfect means that for the given set of keys I have no collisions. That's a good property because you need less logic afterwards to when you insert keys. And minimal means that the memory usage of my container is in big O of my number of keys, right? And some of you, okay, I don't have the internet, so the JavaScript things, but you all can read LaTeX anyway. Or maybe I forgot. Maybe some of you knows about the gperf tool. Raise your hand if you know gperf. Okay, gperf is used in plenty of software. It's used in compilers, it's used for parsers, and it's a tool that you give him a set of keys or pairs of key and values, and it will generate functions that can do the lookup for you and returns either the value or a Boolean if the value is in the set or not. So it's a tool that generates C code that you compile and embed into your application. The input of gperf looks like that. You've got this very flex-like double % syntax, but then you just give all your keys. And you feed that file to gperf, it generates the C code. If you want to do a cross-platform build, you need to make sure that gperf can compile on your platform. It's always a bit tricky to have generated codes into your code base. Well, I do like that because I'm a compiler guy, but It's not always straightforward depending on your build system. So our goal is to emulate that. And in Frozen, you just give the same keys, put them into a structure, and it's as if we had implemented jperf in a constraint manner. It's actually not the same algorithm that runs under the hood. So we have bad news, or I have bad news. The code generated by jperf for these strings is better than the one runtime generated or compile time generated by Frozen. So that may look like a bad advertising. Well, first, I'm not a commercial, I'm an engineer, so I don't care about advertising. Then, jperf does not handle your particular type. It can only handle strings and probably integers, so it's more generic. And then you can feed this extra third argument that disappeared in this slide, which is the hashing function. And I may, instead of hashing my string using all of the elements, I designed a specific hash function that works well for my elements, and I can feed that to the another set, and then I have the same performance as jperf. Okay, so it's not automatic, while there is more intelligence in jperf, but at least you have the control, and it's more generic. So let's move on. So another set. You've got your key, your number of elements, and you've got a hash key. And it's no longer std hash. And I will explain why a bit later. So first, std hash, I'm not sure it's constexpr. And the second, we need some special hashing because we don't want any collision. So there is a bit of algorithm that I will explain later, which is why I don't explain it on that slide. And of course, key equivalent hash needs to be constexpr. That's exactly the same for an ordered map. So not exactly the same. If you have this eagle eye, you will see that the name of the hash is different. It's because I wanted to maintain balance between brotherhood. Okay, so it's actually an alias, a type alias from one to the other, but so you can pick your poison. Assuming it's implemented correctly, if you have a look at the benchmark, it's exactly the same. You're looking for a string, whether it's in the set, in the map, or in the unordered set. I don't like that. Or if it's in the standard library version, or compared to the linear scan. And we are going faster. We are not paying for the initialization process, as we always do in Frozen, and our hashing is faster. So it's not as fast as jperf, but faster than the standard library one. Intuitively, you don't have any collision, and you're not using the same hash function, so there is room for improvement, and that's what explains this performance. And we've got the same kind of performance improvement where you're looking for something that is not inside the set. So that was for the high-level view, and now I will dive a bit into the implementation detail. Just going back to the binary search part, for this code, if I compile it with Clang, why is it faster than the std set version? And the answer lies into the assembly. So Clang and GCC don't generate the same code for this function. But I like the Clang one because look at this branch. Oh no, there is only one branch at line 39. But otherwise, you only have conditional moves. So this may or may not be a good thing. A conditional move is basically the assembly version of the ternary operator you've got in C and C++. So you can imagine that it is a binary search, and we are computing the index, moving the index value until we find the right point, and then there is a final jump, I can't remember why, and we get the final result. So why is CMove possibly a good thing? At first, it does not depend on the branch predictor. It means you consistently will get the same execution time, which looks like a good property to me. Independently of your data set, you will get the same the same speed. But you're introducing data dependencies, okay? Which means that your pipeline may stall because you depend on the result of the few move and addition to compute the next step. So depending on the architecture, it may go faster or slower, but I don't care because I did not write that the compilers had decided that this is the best for my architecture. So, or at least for a generic architecture here, because I did not specify -m arc equal native. But that's good. That's exactly what I want. And that's very dense too. And it appears that it's faster than a red-black tree implementation and a while loop that does a regular binary search. So that's cool. The code, or part of the code that generated this, is this binary search. This binary search, there is a first step that, because the number of elements may not have the right property, I first cut it so that I can divide it like I want. And then the same move appears because of the next iterator creation. So there is no if here. So the compiler may choose to introduce an if, but I'm helping it a bit. And then my function is recursive terminal. So it means that there can be a while loop, or it can be inlined. And because I have a recursion that stops based on the last element specialized for n equal 0 and 1, the compiler actually inlines everything, and I've got my block of instructions. And I'm always puzzled by how this high-level code can reduce into such short sequence of code, of assembly code, but that's why we all love C++, don't we? So that was for the binary search. And then for compile time hashing. So the first thing I did when so I first implemented the binary search because it was easy, and then I wanted to implement an unordered set. And then I said, okay, that looks difficult. There may be smarter people that already implemented that. So I looked for the reference in the gperf implementation, read some paper, and realized that these people are really smarter than I am. Then there are some people that are even smarter because they understand the paper and they write a blog post that everybody can understand and read, and they even provide a Python implementation. So I just have to take the Python implementation, turn it into C++ in a constexpr compatible C++ code, understand it because it's easier to understand Python code than the paper, and then I can explain it to you. So the first thing you do is you take a hash function, and it does not need to be a very good hash function in terms of collision. It's better if it's fast. It can have collision, it doesn't matter. Then from that hash function, you derive a new hash function that gets parameterized. Here, I have a hash function, but with 2 parameters instead of 1. And the second one, the seed, is used to generate a family of hash function. Because there is the hash function with the seed set to 0, and a new hash function with the seed set to 1. And so I have a generator for hash functions. They probably have the same properties, but that's enough. And this hash function is very poor. I found it on Stack Overflow, so it's very likely not that good. But still, that's what I wanted because it's fast. And then I have all my keys, and I hash them with seed set to 0, and I fill my buckets. And I have got collision because it's a bad hash function, but it doesn't matter. Okay, I have my buckets filled. But I wanted perfect hashing. So now I have all these buckets. I sort them by size. I take the first one, the one with the most collisions, and I say, okay, now I will randomly choose seeds, and to fill my final array, the one without collision, I will try to hash all the keys in my first bucket until they have no collisions. Okay? If it doesn't work with seed equal 1, I try with seed equal 10. That's my random number generation. And at some point, I will get no collision. And that's okay because I have a lot of place, and that's my first try. That's my first bucket. And then I try the second bucket. I'm looking for a seed that makes no collision inside this bucket, plus no collision with the one from the previous bucket. Okay? And I put them, and I go on. And you say, okay, but it's at the beginning you've got a lot of space, but at the end you don't have any space, so you're not likely randomly it won't work. But I've been using sorted buckets, so at the end I only have one element in the bucket, so I can just put it into the remaining holes and record that instead of a seed I will use this particular index. And if I do it like that, I have been generating a perfect hash function using actually two hash functions. The first one that sorted out the buckets, and the second one that differentiates between the buckets. And I have this extra table that stores the seed for each bucket, right? I'm not very good at drawing, but once again, on the blog there was a good drawing, so I can explain the drawing. This function hash that does the hashing. For cat and for blue, they give 2. Okay, so there is a collision. And then this function f, which in my case is h, but with another seed. So here the seed is 1,337. I no longer get any collision. Okay, and I'm storing this particular lit value inside my auxiliary table, right? And with that, I've got my perfect hash function. But I'm hashing twice, which is slow. But I have a very fast hash function. So twice but fast compared to only once, possibly collision and slow. In the end, it happens that we're better. So that was for the algorithm. And now I will go into the detailed part of the talk, which looks at some specific part of the library, something that for an expert C++ programmer may look trivial, but it wasn't for me, and it may not be for some of you. So let's go through it, and then I have some use cases. Maybe you have some question about the algorithm itself, or I made myself perfectly clear. Okay, perfectly clear. That's called mind manipulation. Because if I had asked everybody that did not understand, raise your hand, maybe nobody would have react and I would feel guilty. But that seems okay. So my buckets, they have different size. So I would use a vector. But I can't because I'm in a constexpr world. But I have an extra assumptions. I know the extra bound because there is a given number of keys. So if I'm really unlucky, there will be that number of key in one single bucket. So I can just use some kind of std array or bounded std vector, which has a limit size, and then I will grow eventually. So I can have my poor man std vector in constexpr world. So that's credit for Chris Beck. Then I have std array. std array and constexpr in C++14 don't play well together because I can't index them. I have to use the std get trick, and that's not very pleasant to write. So we just rewrite it with the proper operator, with a proper context version. And we also handle, as a side effect, the fact that someone may want to create an empty frozen map. And in that case, you would need an empty std array. And you can't create an empty std array, but you can specialize it to have just the right type def and the right signature. So that's just useless, but for the beauty and consistency, you need it. Then I've been repeating that we need a random number generator, and a good random generator. But we are at constraint time. So at first it seems very disturbing. You can't take random number at compile time. But actually, a random number is just a sequence that looks random. So you just take whatever random number pseudo-random number generator you want, and you either take the seed from the model_time or whatever, it depends whether you want a reproducible build or not, and then it's completely concept compatible. It just will always be the very same random sequence, but what you need is, it's not security stuff, okay? It's just that you want some kind of property on your sequence, and this particular sequence will have this property, if you're lucky, and sometimes you're not. this one got pretty. We had a lot of discussion. For similar, just for high candies, we wanted to be able to initialize our frozen set, just like our frozen map, just like we would initialize our STD map. But that means that we are using initializer list. But what if, instead of 2, the user would write 1 element and then feed an initializer list that is too big? We need to handle that. It turns out that it used to be difficult. So the size member of initializer list is constexpr. So it's OK, I can put it into a static assert. But not, I can't, because S may not come from a constexpr, may not be static. It depends. Constexpr is not always evaluated in constexpr context. So I can't use static assets. But why can I use assert? Why does assert does exactly what I want in that context? If I am in non-constant evaluation mode, runtime mode, which is not a use case for frozen, but let's forget about frozen for a minute. Then, if debug is not defined, I will run for it, and if my condition is not valid anymore, I will get an STD abort. And that's OK, that's the runtime behavior I want. But what I'm struggling with is the context time behavior. But asserts, if the assertion is correct, then the if we evaluate to false, and I will never execute the STD abort. And the way the virtual interpreter of C++ embedded in the compiler to be able to evaluate constexpr works is if I'm not executing the function not marked as constexpr, then it's not an error. I'm not looking at all the possibilities at compile time. I'm just executing the code, and if at some point I've got an issue, then I raise the issue. So if this condition is invalid at compile time, then I will call STD abort, which is not something I can do at context time. So we get an error. The error won't be size mismatch. The error will be calling something that is not valid in context. But that's OK, I've got an error, and that's what I wanted, preventing the user from misusing initializer list. This actually did not work for Visual Studio 2015. So we had a long discussion about how to implement that, but it now works correctly, at least based on Godbolt. So that's how it does. And then you've got this map at member function, which raises an exception. And we've got the very same problem. I mean, first, we are header-only library. So if we are raising an exception in our code, and someone wants to compile our code without exception, which looks possible because Frozen is a good target for embedded systems. I mean, it doesn't take a lot of place, it's all in the read-only sections, then it's possible that they don't want exceptions. So I needed all this stuff. I think it's pretty standard, and you have got all the same in Boost, but I don't want to add a Boost dependency only for these 3 macros. So first, you can define the frozen no exception macro variable to ensure that you will only STD abort and never throw. And then you've got all this compiler-specific stuff that have only been tested on Clang, GCC, and Microsoft compiler. But it seems to be OK. So if you specify -f no exception on GCC, it will trigger these macro definitions, and it's OK, you will get an abort. Otherwise, you've got the throws that you expect because you want to mimic the standard library behavior. So just keep that snippet into your pocket. It can help. Then use cases, because it's all fun and pretty, but there may be use cases. Actually, there is. So the first one, which is not super great, but it's actually a decent use case, is I get some string value, say from std in, and I need to generate an enum based on that. We all have written this kind of code. And then instead of doing strcmp and switching for everything, I can just define my map and map the string to the enum. And that just does the job. So you could use map or unordered map. I don't think probably map uses less memory, and depending on the size, it may be faster or not. You just need to benchmark. I had one user. He reported a bug. I will speak about the bug later. But his use case was very funny. He's got all the code point for HTML, and he wanted to turn the code point from a string into its integer representation. And so he had this big map, and he wanted to match the string to the number. So that's somehow similar to the enum version. That was a very funny use case. Oh, look at the last line. Here, that's a small difference compared to the standard library. It's redundant to write the number of elements and having to count them into the initializer list. So I made a small helper function that just takes the table and builds the map out of it. The good thing is that at no place you explicitly set the number of elements, so it's easier to maintain if you want to add elements later. So then I have got this mail exchange with Chris Beck from Tesla, and you can read it, and I will tell you some bits of my life meanwhile. You just need to imagine. I'm from the countryside in France, and also I don't meet that many C++ developers apart from my job, and I'm working remotely. And it turns out that Frozen is actually used in Tesla cars. So you take, there is fields all around my house, but the code I produced is used into a Tesla car. That's horribly fun. I'm very proud of that. On the way from France to the US, you've got 10 hours to think about example of usage of your library. I like this one. The idea is sometimes you have a function. It's most of the time called for only 3 or 4 parameters. And if you want to optimize it, you can use memoization. That's a typical optimization for a function like programming, but it's generally done at runtime. Like whenever it's called, you have a cache and you record. If it's not in the cache, you compute the actual function and you put the result into the cache. But you could do that completely statically. First, because you're constexpr, you know that you don't have any side effect because you're constexpr. So you already match some kind of purity requirements. And then you statically build for all the value capital VS given as parameter. You let the compiler execute your function and store this into the map. And then whenever you call the function, you will do your lookup inside this small cache, static cache. It's never invalidated or updated, so you need to have some a priori knowledge about the behavior of your function. But you've got this function adapter, which turns any constexpr function into a cached version for a given set of value. I think it's a good exercise to write the var version of this. It probably doesn't fit into a slide, and that's the reason why I didn't write it. Of course, all the method of the std map, of the frozen map class are themselves constexpr. So I can use them in a static assert if I want to check things. It's always useful to have a hash map when you want to reason about a problem, even if it's a meta problem. Then I told you about this bug. This guy with 2,000 HTML entities, and he wanted that into his code. And Frozen was just compiling, while actually the interpreter of C++ embedded in Clang was executing the code. and sorting and trying different versions or depending on the seed and so on, and then it bailed out. It's not because it's too long, it's because the compiler guy says, okay, what if in a constexpr execution context, we've got an infinite loop? It never stops. What if we have an infinitively recursive function? It never stops. So they introduced these flags, which, when you don't know them, it's very frightening for Frozen because it would only work for small values. You just need to put big values and you can compile bigger codes. There's probably a Visual Studio version for that, but I'm not aware of it. And now I want you to think about all we've been talking about for 47 minutes. In fact, there is a class of algorithm that fits very well, or that can be inferred from these small examples. In all the cases, we had an initialization step. And then, because we had this initialization step, we can go faster at runtime. And there's a lot of algorithms that do that. Some pre-computation, there's generally that's the dynamic programming or related to that. And then you've got the execution step, and it goes faster. Any other algorithm that comes to your mind? Probably yes, because you've been to the Hannah presentation this morning. And that's exactly what she does for regex, except it's much more cool for regex than for hashing, but that's another story. So there's a lot of algorithms that could benefit from that. And the nice thing is that generally, when you use this kind of algorithm, there is a trade-off between initialization and execution. But with C++ and constexpr, you change the trade-off. You no longer pay for the initialization, well, if it's on static data. But you don't pay for that, and you only pay for the runtime execution. And possibly you don't pay if the runtime execution can be done at context time too. And one of the first algorithms you may have learned perfectly fits into that topic. You know this kind of sequence and you're looking for a string. And if you do the naive algorithm, then it's very slow, and so you're pre-computing some tables that depends on the shape of your data. And so that's called Boyer-Moore searcher, or there are a few extra ones. So they are available in C++ 17. Just because it was a good example for this talk, I implemented it too for Frozen. And so basically the Frozen make Boyer-Moore searcher is constexpr. So the table is pre-computed at compile time, and then you can just use it. And even if your data is very small, it doesn't matter, because even if the haystack is small, there is no overhead of pre-computing the things related to your key. So you can just go and use that everywhere without thinking, okay, maybe the trade-off is not good for that type of data. And so you can generalize this idea, and I like that. So I told you I was working for Quark's lab, and so we developed, or someone in our firm developed this library, LIF, library to instrument executable formats. And so there is some part of parsing ELF and reporting information about the ELF format. And so he had a lot of this string to enum things or enum to string things. And so using Frozen in his library, it was not a matter of performance, but really it shrinks the library a lot. And he can use the fast searcher to implement a fast mem, which is something reverser like when they want to grep from some data into the data section, for instance. So it's used at Tesla. One interesting aspect of using this kind of configuration compared to standard set or standard map is that you no longer have the static initialization order fiasco, because you can specify your dependency and say, okay, this map depends on this map and depends on this map, and you no longer have this, I don't know the order of the initialization. So that's a side effect when everything is static. You don't need to order the construction step. And then I told you about my daughters. At school, they really love pixel art. They do it on paper sheets, and they feel okay, and they can represent mushrooms or ghosts or whatever. My elder daughter is using Vim and Mut to send her email, so I wanted her to be able to do pixel art using Vim too, and using C++. So this defines a color map. The key are red, okay, green, blue, black, and white. And then she can modify her file. So she is drawing her pixel art stuff. And then, based on the color map, which is actually a frozen map, I can automatically turn this into the PPM format, not JPEG format, okay, but PPM, which is basically like a bin map format. But the nice thing is that when she runs G++, it creates the image into the data, read-only data section of the program. So some people use convert to convert image, but real people use G++ to convert their image. So in the end, she's got his lovely mushroom that has been compiled at compile time. So that's end my talk. Once again, I'd like to thank Chris Beck and Jérôme Duménil for all their work, because it won't be possible without them. Okay, it looks like cliché, but that's really the case. Also, I'm grateful to my to Quarks Lab, because that has nothing to do with code obfuscation, but still I had this 1 day a month where I can write my hobby project, and that's cool. And well, it's on GitHub, it's an open source license, and you can have fun with it. And you can also ask questions, and you come to the Miku and have the question. Yeah? If you don't come, I just repeat. That's okay. The implementation of what?
The perfect hashing.
Mm-hmm.
So that's actually orthogonal to the constexpr, right? Because you could easily have a hash table get the list of all the keys that you'll ever have at runtime and still use perfect hashing. So I'm wondering if, based on the way that you've implemented it, whether this would be easy to do, and whether you have any interest. Because I actually came here thinking that was possible. It is a very, very common use case in a lot of industries where you, at some point in the program, you learn all of the keys you will ever store in your hash table, and you only use it for access from then on. And I've actually been looking to implement perfect hashing for a while. I was starting to think about just doing it myself, but you know, this code has like 99% of what's needed, right? So I don't know if you're interested, or if maybe it's not possible.
So let me rephrase it to make sure that I understood your question. Here, I know all the keys from the start. What if I would first fill the keys and then at some point say, okay, it's fixed, and now I want perfect hashing, and I won't add keys anymore. Can I have perfect hashing from that point? Is that your question?
Yeah, or you know all the keys at once, just at runtime, not compile. Because your hash table size is fixed, that's actually the only thing that is a problem. Otherwise, it would be a non-constexpr.
So the algorithm would work. That's for sure. Then is it efficient in terms of execution time? I'm not sure. So you can make it work, but the thing that you pay only in compiler time makes the thing different. You don't try to improve the construction of this perfect hashing function. And I'm not sure, or I'm pretty sure that's not the most efficient way to build a perfect hash function. Because even for small data, sometimes it takes 1 second or half a second, but that's still a lot compared to the size of the data. So it would work, but I'm not sure that's the best algorithm to do that. Yeah.
How does the duration time scale with the number of elements?
So I didn't do any measurements on that. The problem is that there is this random step where I repeatedly try seeds until I find a hash function that gets me no collision. So if you have a look to the original paper that is cited into the blog post, then you will get an upper bound on the behavior, but I can't remember how it behaves. There was another question around that, yeah.
So it's a mutable library that I hear it, and what type of license?
What? It's BSD license, I think.
It's like open library?
It's open library, and you don't know, it's not viral.
So is it cross-platform as well?
Oh, sorry, I should repeat the question. So there was two questions. The first one was what kind of license it is, and I think it's BSD or maybe Apache, but that's the idea. So it's not non-viral. And the second question was, is it cross-platform? And the only answer I can give is it's tested with Travis for Linux and for Mac, and it's tested with Obveyor for a recent version of Visual Studio. Yeah.
I already evaluated the library on GitHub, and I'd say if you're thinking about integrating it into existing projects, the only downside I see is get another stream file. So that will like crawl into your code base and it will like go into your interface. Maybe it makes sense to add some support for this tree view, which kind of fits to this.
Yeah. So the question is, if I want to integrate this into my library, I probably would use it with string types, and then Frozen has its own implementation, or very sloppy implementation of string view, just because it's C++14. And so yeah, it would make sense to be able to compile, to have an if-def. If it's C++14, then provide Frozen string. Otherwise, just use string view. Yeah, definitely makes sense. Go ahead. Any other question? Okay, so let me thank you again and have a good day. Come to the tour.